Hi, I'm BrendaEM. This is going to be a code review for RDL, and the version I'm looking at is 240. The version you're looking at might be higher, might be lower. If it's lower, you should probably download a later version. First of all, I'd like to say thank you for hackaday.com. I appreciate the nice write-up for my little interference experiment. I also want to say I'm sorry this took me so long to get around to, and I wanted to get the interference experiment out first. I wrote RDL originally because I had a bunch of little programs I used for various stepper motor chores, and just like moving an axis while I was building it. And or one of the things I had in the back of my mind is for winding coils and stuff. But the thing is, I don't build a bunch of machines. I build a bunch of setups and use them and take them apart and reuse the parts to make something else. So I ended up with a bunch of these little programs, these sketches, if you will, of for various things. I didn't know what they did after 6 months. They're all cryptically named. I'm like, why don't I make one program to do more than one of these things? And it just grew from there. And I've gone through great lengths to get it to fit an Arduino micro, and it fits in a Nano really easily. And the thing of it is that if you look at my programming style as it is, I'm not the best Arduino programmer, and I don't even really consider myself a programmer. But I looked at the way that, like, the code I write, I want it to be readable and I want it to be compact. That's what I was going for. It didn't have to be elegant. I have friends who program and can write very, very clever ways of programming things. And although looking at it, it's not always to me very readable. And so I gave up some of the cunning, some of the cleverness, and just tried to write readable code, and with lots of notes, and with the idea that I would share it with people. I wanted to put some more commands in RDL. In order to do that, I had to look at the program and say, what can I do to make it smaller? And so what I was looking for was redundancy. What am I doing over and over again? What am I doing more than, say, two or three times? And so I kind of came up with kind of a tree kind of structure. And so there's a few tiers, of course. And we're just looking at, this is just a list. This is not a program or anything. But what I did is copied and pasted all the names of most of the functions in RDL. And of course you have your setup and your loop. And then I've got a bunch of high-level functions, a bunch of mid-level functions, and a bunch of low-level functions. And the low-level functions, if you look at them, motor microstep, motor direction, motor state, and motor nudge, but they usually have to deal with the actual motor itself, or really the driver. And in the mid-level, there are things that called low-level stuff, but they can be called from the high level and so forth. And this is what I came up with. At the top here, I have the normal stuff like version information, contact information. I try to put links to the videos and stuff for the manual. I have legal information. Under the features, I was trying to show people the features, but also I was trying to teach them the commands too. Under the instructions here and the options, I made a mistake with RDL1, and this is one of those things. I was too close to the project to see it clearly. Some of the original options I had chosen were not the best. So in other words, if you didn't hook up a joystick to RDL1, it would run on, and I'm sorry about that. I also wanted to write the instructions both shorter and clearer, and I put warnings here to because I didn't want to get hurt by anything I do, and I have a change log here, which is always good. You can see I have an include here for the EEPROM library. There's like 1,000 or 4,000 bytes of EEPROM memory you can write non-volatilely, variables to, and I believe you get something like 10,000 write operations and probably an endless amount of read operations. And RDL uses it to store its settings. When you make a change, it saves the settings. So if you unplug it, it should keep its settings. I have, from what I read, it's pretty smart about the way it does it, and only if you change a variable does it actually do it right. And this is basically the same way that 3D printers keep their that use Arduinos keep their settings for as far as acceleration, jerk, and so forth, and its step settings and its extrusion settings and so forth. So what this line is basically saying is I want a constant. So this is kind of a compiler thing, and in the end, this is going to get replaced with a number even before it probably ends up being sent to the Arduino. So it's what this line is saying is I want a constant, and this an integer. I want a 2-byte number, and then I want it to replace every instance of this pin driver primary with the number 12 using an integer. Like many other Arduino programs, I use constants for pin definitions, and I'm glad a lot of people do this because it helps the readability of the program. You can see here that the joystick pin is A0, which seems pretty strange, but it might be a hexadecimal number when it gets compiled. You can see here that I've got a primary and a secondary pin, and that seems a little strange too. So I had a problem. I had some stepper motors that had completely different drivers. Instead of having a step pin and a direction pin, they had a forward step pin and a backward step pin. So the primary pin usually ends up being the step pin, and the secondary usually is actually the direction pin. But on these special motors, I had to try to come up with a system that did both. I use a lot of constants to help the readability, like this one. Whether or not the motor is awake or asleep could vary from driver to driver. In this case, awake is low and asleep is high, and it's a very arbitrary thing, and just using a constant just makes things much even more readable. The same thing with the limits, the e-stop and the home and the limit. These could be either switches that are pulled up or pulled down, or Hall effect sensors or optical sensors, and who knows whether or not what state it's going to be. But so basically, what we're doing is matching up a state of the sensor with what we want to look for. Just like the little title says, this is for range checking, just to make sure that you don't put in wildly crazy numbers, and I want them to get thrown out, like have it do like 5 million steps. And if you want to put in 5 million steps, well, you would probably end up wanting to change these settings. This is for backshoot. And basically, if you're homing a motor with a sensor and you're actually right on the sensor, well, we want to make sure that we're not in the middle of the sensor. We could be at the edge of the sensor. And so what this does is saying I want to back up 1/40th of a revolution, then start looking for the sensor again. So when you use the Arduino joystick, I believe it's got a 10-bit DAC, so to return numbers from 0 to 1023. And right in the center where the joystick springs, there's a 64 sized area numerically where the joystick won't do anything. And then I do some pre-calculations here and stuff, as far as past the dead zone and stuff. And I do this basically for speed, because I don't want to do this inside my loop. This was the mistake I made in a previous version that I accidentally enabled the joystick, and people were having problems with that. I'm sorry again. I've got a variable here, although we have mostly constants here, but I tend to keep things grouped together. And then I have some more readability constants like forward and backward. I don't need to know what numbers they are, and now I can use forward and backward as a variable, and I don't really care. These numbers are really arbitrary to me, and I don't care about the numbers. It's just the idea is forward and backward. Basically, the programming language has to be told which is which, and then it doesn't matter to me. Like rotary and linear and so forth, and you'll see this all go through a lot. And I used to do, like, you would think that you do forward and backward. Well, why don't you use a Boolean for that? Well, the reason why is because a lot of these things, I started off with maybe two values, just a switch, and then I ended up expanding it. And now, for instance, I was basically writing for hardware or software, and then I kept on adding things on the end, like both. I want to be able to do both. So sometimes I tend to avoid booleans for switches. I have some rudimentary error codes here. I don't have many error codes. There's basically 4 error codes. There's no error code 0. Error code 0 will be like no error. I use string objects for text handling in RDL, and I also have some kind of little control things that I use here. I'll get more into that later. I have some other control things in here for like divisions and division and error, and these basically become variables that I use to control the program. And when you print a line from an Arduino, you can control the metissa of the numerical value you put out, and I thought that'd be a nice constant. As far as location, when you type in like go to here, go to there, these are the variables that are used to store those values. This one's largely, these are all global, and this one's largely, basically this is a global that just basically is your current location. And these variables are not quite local, but they're temporary variables to Scratchpad to figure out and calculate what needs to be done. Maybe I could figure out some kind of system without resorting to define a whole bunch of extra variables as local variables, but I wonder if it's possible to come up with a naming convention that can whether or not, there's basically Scratchpad variables, basically like the registers inside of the processor, basically. But I have to think about that. And this portion and joystick increment are for speed. This is more calculation variables, and basically the steps are kept in longs because integers are too small. There's a lot of instances where you'd go over 32,000 steps, or 64,000 respectively. The period variable I use for the run command. The impedance for the stepper motors, basically I consider that there's a certain pulse width that the motor runs, and you can step a motor so fast, and any time you add to that period is basically slowing it down or impeding it, and so that's the kind of mantra I used in my variables, and this is totally arbitrary. And anyway, I have some generic variables here, and you'll see a val f, and all these are just temporary variables, and in places I use a floating point copy of a long variable. So the ability of Arduinos to be able to save data onto EEPROM is really neat, because otherwise you would need to use some other form of non-volatile storage, and you'd probably need an outboard chip, and maybe you could do it with 2-wire interface or something, I2C or something like that. So I did have one problem with it, in that I couldn't use the Arduino string object with the Arduino EEPROM library object. So first I want to say I built this structure, and I have data, and I want to save it to EEPROM, and I had a problem that well, what if I change the program? Then the data in the that's stored in EEPROM might be totally bad, or maybe even dangerous to the user. And so how can I make that safer? Well, I need some way to identify the data, and I also need a way to know if the EEPROM data is just random garbage that's in there, uninitialized EEPROM, just garbage in there, and so I needed a way to identify with it. And also, once again, because I had a problem with the string object working with the EEPROM object. So I did some thinking about this, a lot of experimenting. I experimented with like 2 days to try to get this to work, and I gave up. And usually, if I'm really pushing against something, it probably means that maybe I'm going the wrong way. So to move on, and because I want to write programs in broad brush strokes instead of really getting fussy about it, what I did was I used a long variable. You can see here, there's a constant here for basically a way to identify RDL and its version. So what I did is I typed in RDL into an ASCII converter, and it came up with this number. This is RDL in ASCII. The last 2 digits in this number are actually the version number. So this is what I did. So basically, version 2 of RDL. This is the first 4 bytes that are laid into the EEPROM. And you can see this. This is how I built my little structure definition packet. And so basically, I put this is the definition of the structure. And then later on, I make a setting out of the definition. So that's the kind of thinking as such I'm using. So if we look at this, the information I'm saving the identification. And later on, I'm actually going to put this digit in here in this header. So I'm going to take this number here and put it into this long and save it off, and that will know which program has got this data. Just in case there's some random stuff in there, and which version. And I found that when I'm changing the program, I don't always want to, if I make a minor change, I don't need to rewrite my EEPROM data. So this worked out pretty good, and I'm okay up until, to 99 versions as such. Anyway, so I also save off a lot of other stuff as far as this is mode, whether it's rotary or linear. This is the direction scheme. This is the driver, and this is these are enumerated, so with global variables I might add. So, basically any function you write can access this stuff. Basically, this is the micro-stepping scale, the motor step state as far as being awake or asleep. Then we have a bunch of other motor and driver settings, some smoothing stuff, the joystick stuff, what kind of limits you have, and this is enumerated and also global, I might say. This is the user can type in RPM for using it. Basically, you can make a clock out of it. Not a very accurate one, but it comes in. I thought it might come in handy if you want to make a little display or something like that to put in a store window or something. Who knows? Or something to operate like a pump. Hopefully not a medical infusion pump, but hopefully like some kind of non-life critical pump, to run continuously or to dump a little sand into something. I don't know. And these are also the variables as far as the limit settings. Now we come to the messages. This was one of 2 techniques I used. The other was very common, and that's using when you do a serial print or use the F option, and which I have no idea what it stands for, but Flash, I think. But anyway, it stores the your print statements in flash memory, which are actually likely slower than if they were stored in data memory, but it saves in data memory, which is kind of tight in the Arduinos, at least the little ones. And I wanted this to fit in the little ones, at least with this version. Anyhow, so basically these are a set of constant string objects that get used throughout the program. Basically, if I have any kind of thing that's reported back to the user that I've used more than once, it basically has become one of these. And a lot of these are just normal messages like done, but in EEPROM, read and wrote. But some of them are not so common, like these limits ones and these error ones and so forth. There's section E stop one here. The good thing about these is it saves memory by reducing redundancy, and actually these are quicker than using the F option with Flash, but the bad part is that it's, as far as I know, it's saving data memory. Now we come to the Arduino setup function, and basically this is just code that's called once. You could put anything in here, it gets called once, and then the stuff in the loop, which comes later, gets repeated again and again. So basically this is used for initialization. Most of this is pretty normal. You know, basically I'm just setting all the you know, the limit stuff and switches to inputs. I'm setting all the driver pins to outputs, and this is for the micro stepping. If you look at the Polulu A4988 drivers, you'll find information on this, and this MS1, 2, and 3 matches up to their instructions. Also, there's in Arduinos there's a thing called LED built in, and I believe that might be tied off at a pin 13 on many Arduinos, so I wouldn't use that for too much stuff without checking. And I use that for a status indicator. I begin a serial session here with the serial object in the method being begin and at 9600 baud, because that's unfortunately the normal for Arduino as of now. You can see here that I've used the F, or maybe I can't say it's for Flash, but I like to hope that it is for Flash. But anyway, using this option allows this string to be put into flash memory, which saves on data memory, which is pretty tight on the Arduino, especially the micro and it's a little bit to the nano as well. The only thing is I don't like the syntax for this. I think it's a little cumbersome. Anyway, so basically I read the EEPROM, and using this setting thing again was this structure here, and I get that, and I compare it with my the ID of this version, and so this reads if setting ID header is not equal to ID RDL, which was this constant right here. So if it doesn't find these 4 numbers, this is stored as a 4-byte number, and if it doesn't find this number in the beginning of the data it finds on the EEPROM, then it will initialize the EEPROM defaults, which I'll get to later. So, and it'll print a message read. Otherwise, it'll write them and say that it wrote it. So we want to wake her or put to sleep the motor, and I'll touch in pretty soon, and set up the motor micro steps, and in this little line, so I look for things that can speed up the program inside of certain loops, and this is one of them too. Once you get the information as far as this information, you could do pre-calculations on it to try to make other parts of the program faster, and that's what I did. So I thought this would have been cumbersome to do, like hundreds of times a second. So I figured out my joystick increment, like it says here, for better performance. And so I look in loops and I ask myself what's getting done over and over and over again, and I try to do that outside the loop if I can. And this also becomes a variable, obviously. And I lay down one prompt, and this is the message prompt, and this is actually the prompt message, I should say. And here it's defined as this RDL with a new line character and a colon. So this is the loop function. It's one of the 2 main functions in Arduino programs. There's setup, which are things that get initialized and used once, and then there's a loop, and the loop gets continually done over and over and over again. And as far as I know, there's no way to stop it other than taking your program and putting it inside of a smaller loop that catches it going forever. Regardless, before we get into this, I wanted to look at some of the other functions, and there's a list of them over here, that some of the other functions or routines I use that support the main loop. So let's scroll down to the bottom. At the very bottom here, I have a function called motor set microstep. And this may seem silly. What it does is it takes in 3 bytes, and it does digital writes and the microstepping pins, which we defined above, respectively. So it takes this MS1 byte and writes it to the first microstepping pin, second and third, and so forth. And this may seem silly, but it saves space. Like, let's copy this for a second. And let's go up to the function that calls it, which is usually motor microstep. And if we want to shut all the microstepping off, so if setting microstepping equals 1, then all it has to do is call the other function and give it low, low, low. And which is equivalent to this. And this is actually tools auto format control T. Anyway, so in other words, I would have a block of text for each one of these decisions. I think it's easier to just to have that. And because now I can look at the bigger picture, the bigger picture, the broader brushstrokes are, what am I doing here? I've got to worry about breaking this down programmatically and without having to worry about writing to the metal, as it were. I'm not doing port writing or anything. So, and this could be expanded. I put the tables in here, so, not only for my own use, but, for other people's uses and stuff. And if I add something else, I'll put it here, then I'll look at this, and this is just comments. It's, when you compile it, it's gone. And I'll look out and try to make more decisions off of this and modify the code so it can be expanded. The next function is called motor direction, and you just tell it which way you want to change which direction you want to go, and it does it. And that seems pretty simple, but the only thing is I want to support 2 completely different kinds of drivers. Those drivers that have a step pin and a direction pin, but also those drivers that have a step forward pin and a step backward pin. And the other thing that makes it complicated is I only want to change the direction, as far as the driver is concerned, if I have to. And so that's what I do in here. And as we look at it, you see it says if weight equals forward. And that's why we defined, the constants above. So this is more readable. If weight equals forward, that's a lot easier than saying if weight equals 0 or weight equals 1, I think. And because this is done at compile time, it doesn't cost you anything as far as I know. So if we look in here, we can see there's a delay here. There's a delay microsecond, setting driver delay, which is actually defined in our structure above. And this is only applied if we're actually going to change the direction. And likewise, for both directions, it does that. And then we update, if we actually change the direction, we update our current pulse pin, because this is, once again, I'm using 2 different schemes, and also our current direction. So next time this hits this section, it'll know which way it's facing. This next function is called motor state, and what this does is just wake up or put to sleep the stepper motor driver, and it toggles the little LED that's often attached to pin 13 on Arduinos. And you can see here if state equals awake, and so we defined awake above in the program code. It's actually a global constant, and it's one of those things I think I'd want to be a global and constant. Is everybody on? Even if I was doing this with other people, it's like, could other people be on board here as far as what's awake and what's asleep as far as the driver's concerned? Anyway. You can see here that I also apply a little bit of delay afterwards to make sure the thing's fully awake or asleep. This next function is called motor nudge, and you tell it which pin you're going to be stepping on, and you tell it the length of the high portion of the pulse train and the low portion of the pulse train, which I just call the impedance, and it steps the motor. But it steps it with checking for limit switches and e-stops and a keyboard interrupt. Unfortunately, the keyboard interrupt doesn't work the way I want it to. So basically, if you want to interrupt it, you hit space bar and enter, and send that across the serial port, and it'll stop it. So that's optimal. Maybe that for another version we could do it differently, and we'd have to change basically the serial handling in order to do that. Also, in the Arduinos, I wouldn't, they call it a bug. I don't think it's a bug. I think it's a design decision they made that when you do a delay microseconds, it's not that accurate. Beyond a certain point, I think it's accurate to like 16,000 roughly. I think it's actually an odd number. It's not 16,000, 367 or whatever. But they made a decision, and so if you go over so many milliseconds, or microseconds, I should say, if you go over so many microseconds, you run into problems. So I tried to address it in there. So I have got a variable defined for that. I have a key variable defined as a char, and when I start up, I clear out the error code and assume that no errors happened. And this is a global variable, by the way. And so I did do a digital read on the e-stop pin. And once again, this is global and defined elsewhere. And I see if it's been tripped. Speaking of trips, I've been tripped so many times on this double equals thing. Anyway, I don't know what problem it was supposed to solve, but it causes more problems for me. Anyway, so if the e-stop's been tripped, I just tell it that error equals error e-stop. And once again, these were defined in the constants above. And I print the error e-stop message. And then I do some, I check the limits. And likewise for, obviously, this is pretty simple. If it's, and there's a few modes, and some of them are software. So I've got for limits, I have no limits, I have software limits, I have hardware limits, or both. So it goes through a decision tree in here, trying to decide whether or not it should check to see if anything's been tripped, and so it does that here, and if like if a limit's been tripped, it prints out the message. Likewise, if there's if you type in a space, in this case it's a space, and hit enter, and I wish I could do better on that. I'd have to really change the kind of input command to gather individual characters, but maybe in another version. But anyway, you can also interrupt it by typing space enter, and it checks for that here, and also prints out the appropriate error message. And so if there's no error, then we can step. So that's what it's saying here. If error equals 0, perhaps I could have defined for something for no error. Maybe that would be a good idea. Maybe for the next version. And if there's no error, then it can do this. So it does, it pulses the pin high, and it waits for the high portion of the pulse train, and then it pulls the pin low. And then I do this little thing here to try to get around. This is the magic number, 16,383. And I don't know why this seems like an odd number, but the 16,000s, but usually 16,667, but I don't know where this other stuff went to. Anyway, so if the delay is over this, then I do this little bit of math here to try to straighten it out. And likewise, you can see that if there is an error, we put the motor asleep. This next function is called motor move smooth, and so if you give this function a distance, basically, and some other things, it will move this motor in trying to accelerate gently and move it as quickly as possible, and then lower it gently. If you look to the right, I've got a chart. Let's look at the chart. So you can't take a stepper motor and just make it go full blast speed, and expect it to go as fast as it can without stalling. They will stall if you have very short pulses. They might not start, basically, and I don't think you can ever get a stepper motor going as fast as it can without ramping up its speed. And that's one of the options you can use, is you can use a ramp. If we look at this chart here, so you could make a linear ramp, basically if you imagine a line going from this point to this point, you could just use a linear ramp. But that makes little jerk points here and here, and that's not as smooth as it can be. And although it's very processor efficient, And this is even a little challenge for an Arduino, and I'll get on to it about that in a minute. But so I heard about this sinusoidal or smooth stepping algorithm or way of doing things. And I saw it, and I'm like, I want to implement that. And I'm like looking at how can I implement that? And there's always a speed cost for these things, and we'll get on to that. So what I wanted you give it a number of steps, like this is the steps from here to here, and you want it to speed up as smoothly as possible, run high as continuously as possible. These steps are very short. These steps are very long. And then when you slow it down, you gradually increase the length of the steps. And the sinusoidal nature of it makes this jerk point kind of smooth. But there's a gotcha, and I think I found a way out of that gotcha. So inside this algorithm, I also implemented something to figure out how much extra time the Arduino takes to perform this, this smooth stepping thing. And you can see that there's, if you have enough of a video resolution, you can see there's actually 2 lines here. And there's a little notch between when the algorithm is engaged and when it's not engaged. And what I do instead is kind of compensate and add that that difference onto when I'm not using it in order to make it a little smoother still. Anyway, notwithstanding. So the hard thing about doing this kind of stuff is that you're interested in this acceleration curve, right? And so you're thinking of this area right here, how can I get it going as fast, as smooth as possible? But oddly enough, when you're talking to the motor, you have to be thinking in kind of a negative space, and you're thinking about how many delays you're going to put on the other side, Like the first step, you can see, like this is the total, what I call the total impedance. This is just a name I thought of something. And so basically this is the low portion of the pulse train that the motor sees. It's the low pulse. We do a digital write to low. So this is the total time. This is the time this is the delay that the algorithm adds on, and this is the minimum delay, or the fastest the motor would go. Right here, the delay is as small as it can go, and or short as it can go, and the motor is running as fast as it can. And you can see here that the delay would be very high here, and the delay keeps on getting shorter and shorter and shorter. Now the motor is going as fast as it can, and this is your minimum delay or impedance. And then when you want to slow it down, the delays get longer and longer and longer until finally the motor stops. There's also a couple points that I define, like, I didn't put it here, but you've got like a start point, and you've got a sustain point and a decay point, and there's like an end point in here. And so the algorithm is in place during this kind of S-shaped curve, and it's not in place here, and then it's in place here. And once again, I have a little bit of compensation here to add more. I actually add this in right here, the delay right here. If you look at an oscilloscope, it might work pretty good. I might even have to recalibrate it again. There's actually comments in the code if you want to recalibrate it for your particular Arduino, or actually like a Tinsy 3.5 or 3.6. This delay would be negligible. This system you probably wouldn't even need it, but it might make it smoother still, I should say. And so I was looking at this. How can I generate this S-shaped curve? And so basically it's made out of a sine wave, and I'm using different portions of a sine wave. If you look at this portion right here at the bottom here, it kind of looks like this right here, this 270-degree portion of a sine wave. So this is kind of a representation of how a sine wave would be generated or plotted and stuff using the sine function. If you're doing cosine, I believe it would start off here at the 90-degree point, either before or after, I'm not sure, but off the top of my head. But however, so if you look at this 270-degree point, that's corresponds to this. So I start this at 270 degrees, and I go up to, and I can get two sections. I can go from 270 past 360 right up into that point, and that gets me from going from down here along this line right up into this point. And then I switched the function, not the function, but I switched the algorithm out of it, and I just sustain it. I had a little extra time too, and I'll show you that again. And then when I want to slow down the motor, if you look at this right here, this looks a lot like this. So this looks like this 90-degree thing. So now it looks like I'm going from 90 degrees down to 270 degrees here. And this is the number of steps. And but the only thing I haven't shown is that there's actually a point right in the middle where you see this 0 line here that corresponds to an imaginary line drawn right through the center of this right here, which I neglected to put. But if you can imagine a line, the smoothing quad height right here would be the 0 point here. Now back to the code. Motor moves smooth. You give it a stepping pin, and you tell it how many steps, how many total steps. If you look on the right, you can see this is the total steps it will be traveling. And then you give it the pulse width. What I call the pulse width is just my name for the high portion of the pulse train. So how long is that? You know, what's the quickest high time that you want to use? And then you give it what I call the minimum impedance. And that's this area right here. And this is the fastest the motor could be going. And also you tell it how much smoothing to give it, and this is this is the amount of the delay that you'll be giving it, and additional delay that the smoothing algorithm will add. And then you tell it how many smoothing steps do you want this to take place in, and I should have put that in here too. This is the length from here to the sustain point. So how wide do you want this kind of this beginning of the envelope to be? And I also used another trick. I noticed, like, why would you want to accelerate the motor faster or slower than you want to decelerate the motor? So for RDL, the acceleration and the acceleration curves are exactly the same, and it saves programming. Let's look at some of the variables and constants. The first one you see is latency compensation smoothing. And so basically what it's saying is when this algorithm is engaged, if you look here, this area, it's engaged. Here, it's just sustaining. Here, it's engaged again. But while it's engaged in this area here, because of the complex math of sine waves and other mathematical functions, that it takes 149 extra microseconds between steps added on. And that's not a big problem in that we have, the motor can only go so fast anyhow. So hypothetically, we could just strike some off of the minimum. But there's a problem with that. And the problem is that this area right here, there's a 149 microsecond jerk point where the motor's going one speed and the next step is much quicker. And I've seen tests where they took a glass of water and put it in a linear way, and it moved. And so I noticed mine had had less smooth movements, and so this is my way of trying to compensate and for that, for the inefficiency of the algorithm. Hypothetically, if you had like a Tinsy 3.5 or 3.6 or something faster, then it wouldn't make that much difference because it could do the math much quicker. And but for the Arduinos, it does take 149 microseconds to have this engaged, and that might make it a little bit rougher. The next constant is smoothing threshold, and what this is for is if you look at this where it says steps, and if you're doing less than, say, 17 steps in this case, there's little point in using this algorithm because these things are going to be almost like a straight line anyhow. And so what it does is use the fallback delay and or fallback impedance, and that's much longer, and so it steps slower. But at the same time, I'm not even sure this algorithm would work correctly below 16 steps. The next one is rad, which is the proportion between radians and degrees. And I also make some equates here for the sustain point is also the length of the smoothing steps. So here's the sustain point, and we also copy this length right here. And the decay point equals steps minus smoothing steps. Here I make floating point copies of some of my variables, and I do that because I need the floating point variables for the sine function and some other mathematical accuracy, but I don't want to use those for control because it slows down the algorithm. Looking at the waveform block, if you look at this first line, this attack angle equals 270 times rad, well, what the hell am I talking about? Well, if you look over here at the picture, remember that this 270 corresponds to this 270, and this is where we want to begin our waveform, right here, like this. And that corresponds to the beginning of what we want, which corresponds to the amount of smoothing we want to add on. So, and then we just multiply it by times this figure we put in up here to convert it to radians, which Arduino can understand instead of degrees. And likewise, this decay angle equals 90 times rad. If you look at the 90 here on the right hand side, this looks a lot like this. Well, it's the same. This is what we're after when we do this. So I pre-calculate both of these. And this attack angle step equals 90 divided by sustain point flow times 2 times rad and so forth. So what I'm doing is figuring out how many steps I want to make this waveform in, because this is an infinitely smooth curve I'm generating. I only have so many steps in which to do this, and so each step this changes. And what I'm doing is figuring out is dividing this waveform, or the amount of degrees in the waveform, by the number of steps I have to perform the operation. And this smoothing quad height equals smoothing times 2. Well, here's our smoothing quad height right here, and if I draw this imaginary line, so what we're doing is biasing we're biasing this waveform. I have some other variables. I have a tick counter, which I increment through the steps. I've got an impedance variable and a smoothing and impedance variable. The impedances, I just consider this area right here, because we're really talking about the delay between the steps. And for the greater purposes of understanding the algorithm, I'm going to gloss over the calibration lines. So here we go. We use our tick counter to count from 0 to the number of steps, and we keep on bumping up this, incrementing this tick counter. So this tick counter is going this way, and our tick is actually looking at a time slice this way if you're looking at the picture. And we reset the smoothing impedance, and the first decision we come to, if the number of steps is greater than the smoothing threshold, we'll do smoothing. If not, we're just going to drop down here, so we can kind of lasso that one. And if we're not going to be smoothing it, we might as well use the setting motor delay fallback, which is a much greater amount of delay or impedance, and therefore the motor goes slower and it's safer. So this once again, this algorithm will not work efficiently if it's less than, say, 16 steps. Our next decision is, well, say, okay, we're going to smooth it, right? And our next decision is, we're asking it questions. Is our tick, or our time slice here on the right, is our tick less than sustain point? Are we in this area right here? Here's a sustain point. Is it less than this? Or is it greater than the decay point? Here's our decay point. Are we going to be smoothing? And if we're not, then we might as well use the minimum impedance plus the latency compensation smoothing. So if we're not smoothing in here, or smoothing in here, we must be sustaining in here. And we'll just use this minimum value you can see right here. And we're going to add this little bit right here to try to make it smoother. And it compensates for the slowness of the algorithm. So we're still talking about these little vertical ticks. We'll draw one pretty close to the end right here. And if our tick is less than the sustain point, let's see, here's the sustain point. It's less than the sustain point, yeah. Or, this is the operator for or, if the tick is greater than the decay point, here's the decay point right here, and it's not greater than that, but it is less than this, then we got to smooth. So once again, we look at our tick point, and we're going to break it up again. This may seem redundant, but it actually helps in the smoothness a little bit to make it consistently and balanced. But if our tick is less than our sustain point, which it is once again, then our we have this little formula that get the smoothing impedance. But so I start off with a tack angle, right? And I need to, which is a little more than 270 in this case, because we're right about here. But we take the sine of our tack angle, and we scale it by the smoothing quad height, which is a little line about there. Now it makes it vertically, in this case, more or less, you can think of it as vertically about this big. And also we take our smoothing quad height and subtract it, and that biases it. So it's actually biased to where we want it, because it's not enough to make this form. We actually have to position it vertically this way where we want it. And then we take, now we need to bump up the attack angle, which was originally 270 because we started here. And now we take the attack angle and we bump it up by how many segments we broke this up into, which was determined by the amount of steps in this area right here going across this way. And likewise, the decay is almost the same thing, but using the decay angle and the decay angle step. So this works almost the same way on both sides, but we're talking about a different portion of the sine wave like we saw before. And once again, our impedance, our impedance is our minimum impedance, which is right here. This is the fastest the motor could go, or the shortest delay possible for this motor just before it explodes into little pieces. And we add to that the smoothing impedance, which we just calculated here. And then we nudge the motor using the pin, the high portion of the pulse train, and the low portion of the pulse train. And then if there's an error, we brake. If not, we keep on bumping through this, and it keeps on basically creating this. And then there's a little decay area. There's a little sustain area, which adds the little tiny infinitesimal little delay here extra, just because this algorithm, like many smooth stepping algorithms, takes time, and then it keeps on proceeding here, smoothing until we get to here. When I was going through the code looking for any kind of redundancy, I stumbled across these next three functions. The first is check software limits. So basically, I use this kind of a system as such of variables that you put where you want to go in the variable location requested. And this function checks to see whether or not that will put you outside the software limits. And it returns true if that's the case. And that's basically all it does. Is first it resets the variable limited to false, and then it checks to see whether or not it even needs to do anything as far as its whatever limit mode you have set. And if there's a limit mode set that applies to software limits, then it checks to see if it's less than start or greater than end. And if so, it returns true. It returns true, and it gives you an error message. These next two functions also removed a whole bunch of redundant code in RDL. The first is seek absolute, and the second is seek relative. And as you can guess, that one does relative movements and the other does absolute movements. And so basically like this, we give it a location needed, and we calculate how many steps we're going to need and which direction we have to go. You can see over here where you have to figure out which direction we have to go. It sets the motor direction using that function we already discussed, and we figure out the total impedance. And because you can also set this setting user delay, you can also use a multiplier to slow down the motor additionally. And then we call motor move smooth, and which we've gone through and given these parameters, and it does the movement. And there was no error, then we change our location to the location we wanted, and we show the statistics, which will be coming up. So these work almost the same way, except for you can see the math here, and the math here is a little bit different. There's a little issue with, I believe it's the ABS function in the Arduino. I don't think you want to do a lot of math inside of it. There's one type of math I don't think you can do inside of it. So that might be a gotcha. So this saved a lot of code. The next three functions are also strongly related. The first is div update. And whenever you do division in RDL, whether it's linear or rotary, it invariably calls this function. And but the thing is, there's three different ways it could be called. You could, like, if you're doing division, you can hit a plus, or you can hit a minus, or you can hit a slash and tell it which divisions you want to go to, or you can hit the joystick. So I wanted some kind of handler that can be called through several different means. And once again, I'm trying to keep this program compact. There's a lot of variables in RDL have special meaning, like location requested, location needed, portion is special. Maybe I should have prefixed those to know that they have special meanings. Some of them are very temporary, and some of them are very permanent. Maybe the whole local and global thing came to be because there wasn't a way to specify whether variables, whether they were temporary or permanent and stuff. The problem comes that I feel that the code sometimes like I broke this function out. I took it out of the middle of a loop and I made it an external function. But if I set this up with its own private variables, I worry that it's going to take up more memory and a lot more code. And so that's troublesome. And I wish there was a more elegant way to do it. I wish I didn't have to resort to these means, to save memory. But maybe also I could have prefixed my variables, and maybe in the future I'll do this. Maybe prefix my variables like maybe I use G for globals or something like that, although it looks ugly at times. Or maybe or maybe temporary variables should be, cordoned off. Because that's how I look at it. I look at it like there's like setting variable. There's basically a setting structure that's also global, and and kind of the analogy I used for writing this was assembly. So assembly, you have entry conditions and exit conditions for all the routines, and that's what I was kind of going for. Maybe there's a more elegant way. I don't know. Anyhow, it works. So basically, once again, we check to see if it's rotary linear. It works a little bit different because the linear supports divisions that are greater than one turn. Rotary, your division is always within one turn, so they have to work differently. And so anyway, and so basically, what this does in the end is we do our calculations. And we call seek absolute, which we saw before, and just tell it the location that we need. And this is why I think that having clear variables, it really helps and stuff. Like seek absolute, location needed. I mean, it just drops into the next function. And so the other two functions are div previous and div next. And so basically, we just check and see how many divisions we have, and we see that if our divisions are at 0, then we're not dividing. Otherwise, we check to see what division we are, and we decrement it by 1 and call div update, which we just saw. And div update in turn calls seek absolute. So it's not really spaghetti. So what I was going for, once again, is like assembly routines, and very atomic little kind of things, and it's more like a kind of a parent-child relationship, and that's what I was going for. Anyway, either of these, it either adds one onto the division or subtracts one from the division and calls div update. The next two functions just report information when you're using RDL. The first is called show sets or show settings. So what this does is after we give it a little bit of just a little title thing here, and this message separator was the little thing with a lot of dashed lines, and this saves a lot of space, and you can use it often just to kind of make the reporting a little more. I'm not going to make a spreadsheet out of it, but can make it a little more understandable. And basically what this does is it goes through the settings structure that we created above, and it goes through all of its little members like motor state and mode and dir scheme and driver and so forth, and report the contents of those variables. A few of them we have to make decisions on, like this of driver equals. Well, fortunately, we made a constant called driver A4988. So we can just say if setting.driver equals driver A4988. Well, we know what's going on, so if it equals that, then it's this. Otherwise, it's this other driver, because I only have two currently. And if I add another driver, I have to remember to update this. And once again, we just follow through and report all the contents of the members of the structure, and so forth. The next function gets called a lot. It's called show stats, and it shows statistical information. And a few of these are from the structure that we defined above, like this member motor state. A lot of them are just volatile kind of information, like divisions. Like when you shut off the Arduino, divisions will go away. But a lot of the others are like the mode will stay, and because it's saved in EEPROM. And I just displayed its information. And you can see here, and I didn't notice originally, but we'll look at this one print line. And we can put our location here, which is a global variable. And so I've got this where it says Matissa. Up above, I have a constant of Matissa equals 6. So I've got a line above that says constant integer or int Matissa equals 6. And so I could change the reporting, or you could change the reporting just by changing that 6 to, say, a 10, if you want a 10-digit nice calculator Matissa. Although, as far as I know, the Arduino, even with its double precision math, doesn't seem fully implemented. I don't believe it can show, or I don't believe it has more than 6 digits, meaningful digits, I should say. And I think the rest is just interesting. The next function gets called as soon as you start RDL for the first time. It's EEPROM write defaults, and most of this is we're taking, we made a structure way up above, and that happens to be global because actually I think it's easier anyway. And so we take it. Here's our structure, basically our structure, and we take its member variables and we change them into variables that we like. And most of these I set pretty conservative and safe. I wanted the user to be able to get a Plulu, A4988 driver and maybe a smart fun little stepper motor or something off of eBay or something like that, and hook it up and have it work to some degree without stalling. So for instance, the pulse width and the delay are set pretty high, and anyhow, we set the variables up to be what we want, and I wake up the motor, I set the micro stepping, and then I write the contents of this settings struct to using the EEPROM method. And this 0 here is the address, the first byte. It's going to drop. It's going to start starting from here. So it's going to take this ID header, which is a 4-byte number, and drop it on the very first byte of EEPROM, and so forth. So it just lays these down, starting from the top to the bottom, and starts laying these down, given the data width sort of variable type for all these variables. And then I also I did a position reset, which is a little tiny routine. You can see location equals 0, steps current equals 0, and that actually saved just a few bytes of code, and why not? And the other thing I did was I made a concession for speed. I do a pre-calculation for the joystick to get this out of the loop. And RDL also does, when you first start it up, if you're not writing to the EEPROM, it also does a joystick pre-calculation, once again for speed, but if you're not writing, I needed to do that as well. This next function is called line input. When I wrote RDL1, I inadvertently set up a system where I could expand on it later. Let me explain. So all the serial input, RDL1, was done through this line input command. And I originally imagined it being kind of like an old basic style line input command. And but the thing is, it couldn't take our arguments. And so you'd have to type in like go to and hit enter. And then you'd have to type in 5 and hit enter again. And what I did was replace it with this kind of stack-based system where you can type in go to space 5 and hit enter. And what this thing is doing, and this gets a little complicated, is there's a lot of swapping going around. You can see this. I use 3 different variables to keep track of the commands in RDL. One is command. So when you type a command, it goes into the command variable. I also use a command copy in like 2 places in the program because I had to, because I didn't want to kill the original command, because I'm taking the command and breaking it down further. So I've got my command and my command copy I use sparingly. But when I wanted to do, I wanted to be able to handle arguments, and I figured the easy way is because I'm doing all the line input anyhow from the same command, is hook up a little stack-based system. So the first thing I'm going to do is print out a prompt, and we do a serial print line and tell it to print out the prompt. And when I first start RDL, there's no arguments. I set the argument variable to 0. And it'll come across this line of arguments are greater than 0. Well, they're not. So what it's going to, because we initialize them to be 0. And unfortunately, they could have been -1s somewhere along the way, if something went wrong. So just in case, if arguments are not greater than 0, they could be -1. Let's just make sure the arguments equal 0. So we do that. The next thing we do is we look at the serial port, basically. And what this command does right here is it locks up the serial port until there's a line of text available. That's all it does. It'll repeat everything inside this loop here of nothing while there's no text available in the serial port. Imagine, if you will, we typed in a command. We'll make our command, let's see, I'm going to insert a carriage return here. We'll make it kind of obvious. We'll type in set home at 100 and a Y. So what this would do is set home at 100 and enter a Y for yes, we want to do it. And it's a little weird typing in the are you sure part of this, but let's imagine we did that. So first thing it's going to do, it's going to take this count variable and it's going to look at our command, which we got from the serial port, and it's going to look for the index of a space. So it's going to keep on, it's going to start from here going across, and it's going to find out, hey, we found a space right here. We found a space right here. And if it doesn't find a space, it's going to skip over this whole thing here. But if it does find a space, and you can see if count is not -1, so if it doesn't find anything, it returns a -1 for some unknown reason. Anyway, so imagine, if you will, it found a space, because it would find a space right here. And first thing it's going to do is it's going to take a substring of count +1. So it's going to take this portion of it, count +1. So here's our count. It would find a space here. It will take everything here, which is count +1, and put it into our first argument. And then it's going to take our command, looking at our command, it's going to take our command from 0 to up into the point where it found the count and basically truncate it. And what we're going to do is bump up the argument counter. Then it's going to take and look for another space. So it's going to look at our argument 1, which was this portion. Let's cut this out. So now we trimmed off, remember we had trimmed off our command to be set home at, and our argument is now this. So this is our first argument. And we can actually make this like this, like command, and we can put argue, make that a argument. It would be argument 0. Anyway, and the next one would be argument 1. Anyway, it's going to look at our first argument, right, which is 100 space y. And what it's going to do, it's going to look for another space in it. And so you can see count equals argument 0, index of. And this looks cumbersome. So basically, this is just an index. So this is just the first more or less member of an array. And there's another word besides member you're supposed to use, and it's not off the top of my head. But we're going to look for another space in argument 0. And if we don't find one, we're going to drop through this. If we do find one, because we would find one, we'll find one right here. So once again, it's going to do almost the same thing. It's going to make argument 1 now. Let's make argument 1. It's going to make argument 1. It's going to make it from the point where it found the space on. So it's going to be, all we're going to have left with is the y. It's now going to take argument 0 and truncate that. So argument 0 is argument 0 substring, and we're going to take it from the first character all the way to where it found the first space. And now we're going to bump up the argument counter one more time. So what have we got? RDL prompt, I type this. I want to set home at 100, and yes, do it. Like F for force, kind of like that. And so what happened is our command became set home at. Our argument 0 in the array became 100. Our argument 1 in the array became y. And the argument counter, arguments, became 2. So when set home at runs, it's going to want some more input. So it runs line input again. And it runs across this line here if arguments are greater than 0. Well, what are arguments? They're 2. That's greater than 0. So what it does is it copies argument 0 into command. So let's see what argument 0 is. This 100 becomes the command, the next line of text it wants. Okay, we did that. And if arguments equals 2, well, arguments do equals 2, then it does it additionally. And basically, these are pops, just like plates in the diner. Argument 0 becomes argument 1. So here's our command became 100, and argument 0 becomes argument 1. And so we haven't done anything to this, but nor do we need to. And now we take the argument counter and then decrease it. We have one less command because we just took one off the top. And that's how this works. So we're at the main loop. You've already seen most of the program, oddly enough. A lot of what remains is just kind of fluff. It's text processing. A lot of it is just visual to show the defaults, and we have some joystick routines and stuff like that. The only thing is, a lot of this stuff is self-similar, and but there's quite a bit of it, and I won't go through it all. We'll go through a couple representative examples of, for instance, for the settings. First thing I do is I lock up the program, waiting for the serial port to become available, and that's what this line does here. I reset the argument counter, do you remember with that? And I run line input, so we're getting our very first command. So I want RDL to be responsive. It's kind of big for especially on Arduino Micro, it just barely fits by like 5-7% or something like that. And I want it to run fast because I've got to support a joystick. I want a person to be able to move the stepper motor of the joystick. In order to do that, I have to have good response time. And it also accepts commands and settings. So there's 3 main things. And the first thing I can do is, if there's a command, I can see if that command starts with set. And that's just what I do. I take this command string object, and there's a method for their string object called starts with. In this case, I look for set. And right there, I've caused a 33-66% split of the processing time. So all the settings will be inside this bracket and so forth. So we've already found out that the thing the person typed in was a setting, and we've kind of relegated or cornered the program into looking at all this possible settings. And I'm not going to go through all the commands. We'll look at a couple and see representative ones and see what's going on. The first one is set defaults, and I always put a comment for each one. And if command equals set defaults, and then obviously we're setting defaults. And I run my line input again, and I give it a prompt. I give it the prompt, and so everything in here is a prompt for line input. And it prints this out. And I try to do a little string processing that showed us that our default has a star. So it's just kind of, it looks a little cumbersome. I had to double escape the slash here. And so more or less, if the command that gets returned is a Y, then we call the EEPROM write defaults. And now we show settings. So you can see why I wanted to show you this kind of service routines, and the functions that support this program first. Otherwise, if they put in garbage, then we print out an error message we've predefined above. And I also do this thing just to make sure command equals command done, which is the same as typing in two quotes that are touching. We'll look at a few more. This next one is called set mode, and once again we put an else if because it helps performance. And once again the case switch statement is faster, and it'll probably be faster also using numerical equivalents to the commands. So, but then we'd have to do additional string processing anyhow. So I figured it'd be just easier to do this. Anyway, we do an else if command equals set mode, and so now we look at our structure that we made above, and we look at its member mode. So if setting mode equals mode rotary, and we had predefined this as a constant above, and this is why constants are great, because it makes it readable. If setting mode equals mode rotary, then we do this, otherwise we do that. So in this case there's only two options, and once again I'm using the F thing, so this will fit into flash and take up less data memory. And I've got, this is only the prompt, and it looks a little complicated, but I wanted to show the default. And we do some text processing, and in this case, because we've done everything except for this little quote thing, I do a line input here, and once again, our line input command is behind the scenes is actually taking our commands, our commands and putting them into arguments and vice versa. So it's handing us the next bit of text that it has for us. And if the command is either R for rotary or L for linear, then we do this. And what I was trying to do is eliminate all the extraneous garbage that somebody might put in, because it's safer. And so if it's either of those, we reset divisions to 0, and we make a decision if command equals R, then val becomes rotary. And val and valf are just temporary variables I use through most of the settings and so forth. And then we change our member variable of our structure setting to the value, and then we do an EEPROM put. And once again, this is at the 0 byte, and we put a whole structure. However, the Arduino in turn just compares it to what's in there, and it only writes those bytes that are different. And otherwise, we tell the user that we've written to the EEPROM, or we give them an error. And once again, I do this just to make sure that there's no problems. And once again, most of these settings are self-similar, and they follow the same structure. And I want to look at this one called set microstepping. And so once again, else if command equals set microstep. And I built this thing because I was afraid that the power of doing it, stepping through powers of 2 might have little problems as I add more drivers. So I did it this way. But you can see I tried to show the user what the default or the previous setting is right here. You can see there's a star next to it, and that's what this is. This is just a line of text that gets printed. And in here, once again, I tried to exclude everything except for what I'm not looking at. So in other words, the user can only return 1, 2, 4, 8, 16, and 32. Otherwise, because what we're going to do is we're going to convert the command into an integer using the int method of the command of the string object, I should say. And once again, I'm using val for temporary variables. And because we're doing this, we have to be careful to make sure there's only one of those things that it could possibly be, because we're not storing text, we're storing variables. And there's an additional prompt asking if you want to set the scale. And once again, this is just the prompt that's get printed from line input. And once again, if it's the command returned is Y, and once again it might just be taking stuff off of the top of the stack of line input. Then we we scale the steps if we need to. And also, every time we change certain parameters, we have to recalculate the joystick increment, and we'll get to that. And we set the microstepping to our val, which is a temporary variable, and we adjust the motor microstepping to the physical hardware. Then we do another put, and once again byte 0, and our whole block of settings, which get compared automatically. And then we if it's successful, we say to the user that we wrote it. Otherwise, we tell them that there was an error, and once again, just to make sure we kill our command more or less by putting in this equates to be equals that. So that's the same thing. That's what it equates to above. And as you can see, as I was saying, most of the code and the settings are very self-similar and a variation of theme. And unfortunately, they're just a little bit different enough where I don't think I could come up with one manager, as it were, to handle all of these cases, because there's different kinds of information we're taking care of. Sometimes we're taking integers, sometimes we're taking in floating point numbers, and we have to make sure that anything that's not appropriate gets excluded, because it also becomes a safety issue. Now we come to the actions, and because none of the actions begin with the prefix set, S-E-T, that they're not kind of locked into going through that branch of the decision tree. One thing I like about the Arduino is that, like if you look at this, if command equals divide, well, I'm not a big fan of the equals. One thing I do like is you don't have to use, so in processing it would be like this. And this does not read as well as this to me. I mean, I can see this from a mile away, as it were, even with my vision. And I like that. Most of this is, except for the exclusion of pointers, is very C-like more than C++. And one thing I like about C is that a lot of the functions can be kind of naturalized, and so we can concentrate on the code. Anyhow, so we check to see if we're dividing, if divisions equals 0, and so if we're already dividing, then I drop the user down here where it says message error not while dividing. I don't think that users would want to divide while dividing, or initialize another division while dividing. I'd envision this program also to be used kind of over, like if you have a manual mill, you can use it to do division. And I didn't want someone scrapping out parts because they accidentally typed the wrong thing in while they're dividing. Dividing on a manual mill looks really hard with all the dividing plates. Anyhow, so I do some string stuff here. I grab my temporary variable val from the line input. I do things differently as far as this is rotary or linear. Linear is down here, and here I do a lot of resetting of variables and stuff. Once again, I use this little tiny stub position reset, but I use it kind of several times in the code. So once again, anything to save space in this version. And I set the number of divisions to val, and I set the current division or just division to 0. And basically this is more than just saying how many divisions. It also, as you can see, it also checks to see whether or not we're already dividing. So this is one variable, this is one variable with 2 uses. Anyway, we do a linear division, and we have a double and in here, and also I've got this inside of some nested brackets, and I want this operator to be forced to be done first, rather than spend my time with an upside down t-shirt that has the order of precedence. I would rather just force the order of precedence that I want. I find it to be easier that way. And this is not right, then we're going to print an error message, which is limit range. And I got a lot of use out of these little error messages, and I broke these particular ones out because they're used a lot. And we can see that basically we're just setting up the initial case for the division, and then really nothing really happens until we run div update. And once you run div update, then because we had set the division to 0 here, then we start dividing, and to give it on which mode we have. Rotary division is different because I think that someone would leave the part in, and I think that linear division you probably want to move to the origin. The next 3 commands are for division as well, and they're pretty small. The first 2 are very small, and division previous and next are called by just typing in a plus or minus while you're dividing. And basically these just call div previous and div next, and those in turn basically end up calling division update, and once it increments or decrements the counter. And the reason why these 2 commands especially are so small is because I wanted a user to also be able to change the division by using the joystick. So I couldn't or shouldn't, or I didn't want to have very elaborate code in several places on the top end. So I moved the, if you will, functionality of for that, or the code for that, lower down, and I showed you that. For division seek, basically, which is just typing in the division symbol. First of all, we make sure we're dividing, and if we're not dividing, we drop down here. You probably notice this, but if you highlight this brace, it'll show you that matching brace, as long as you have one. And in this case, this will drop down here, and we can print out an error if we're not dividing. Otherwise, we just make sure that we haven't go less than the first division or greater than the last division, and then our division becomes the val, which we got here, which was a method of their string object for command, and then we just do a command equals done, command done. And now we come to division end, or div end, and basically we just want to make sure that we're dividing here. If divisions are greater than 0, and if they aren't, it will drop down here to this else, which will print out a warning message. Otherwise, we kind of want to make sure that the user really wants to end the division, because if you did use this program on a manual mill or something of the sort, and you don't want to lose your place, so we ask the user, if they want to end the division, and the default would be no. This is just kind of a text line that the user sees. And if the command equals yes, then divisions equals 0. That will stop the division, and we print a message, division ended. And otherwise, we print a message saying that you didn't okay it. The next command is home, and the user would just type in H. And first thing I do is check to see if we're dividing. If we're dividing, then this variable divisions would be greater than 0. And if so, then of course we'll do everything in these braces, which is print out a message saying that we're homing. It will set the division to 0 and do a div update. And once again, div update does a lot of work for the main loop because it's kind of lower down. And otherwise, we have to decide if the user is in rotary mode or linear mode, because if the user is using linear division, I want it to return to the home position. But if the user is using doing a rotary but not in the kind of division thing, that I want the motor to go back the shortest route possible, either forward or backward. And so that's what we're doing here. We check the setting mode and see if it's rotary. And if it's rotary, it will do everything in these braces. Let's see if I can scroll up that. And once again, I do some math here, and then I had to make like 4 decisions in this. You can see them. First of all, I had to see if we were past 0, and because the numbers could be negative as well. And next, I wanted to see if we're more than if we're less than halfway, and then I'll either move it to the motor to 0 or 1, and otherwise it's kind of funny that there's an interesting story that my friend thought that this could be done with less conditional programming, but I couldn't make it work. Anyhow, this is what I did. And down at the bottom here, once again, I do a message saying I'm homing, and then I do a seek absolute with the location requested, and then I do a position reset. And once again, there's our traditional command equals command done, just to make sure that all these other decisions are made as quick as possible without trying to find the same command twice. The next command is auto home, and it's just invoked by typing in AH. And once again, the first thing I do is check to see if we're dividing, and if you're already dividing, this is not the command you want to type in, because you'll likely get lost. The next thing I do is I do a digital read on the homing pin, and because you could have switches that could be wired as pull-ups or pull-downs, because you could have optical sensors and so forth that could be high or low when they're tripped. This is why it's good to use constants for a lot of your states and stuff like that, to make the code more readable. Anyhow, if the sensor or switch is already tripped, in the case of a switch, the switch might be bent underneath the pressure of the whatever pushes it. In the case of a photo interrupter, that the photo interrupter has a blade that has a certain size. It's not infinitesimally small. So what I want to do is I want to, in this case, set the motor to go backwards, and I want to keep on looking to see if it's tripped while I'm backing up. And then also I want to make sure by taking a few more steps, I didn't want to have a case where it's kind of partially tripped. In the case of the photo interrupters, some of them have built-in comparators, but you could end up with kind of a noisy thing. But anyway, I wanted to back up a few more extra steps, and to make sure that you've gone far enough to get a good reading now, then when we go forward. And this is kept in the variable home back shoot. And once again, if you look here, I do motor nudges using the pulse pin, the pulse width, and for the delay, I use the fallback delay, which you get to use for a few different things. Now that we made sure that the switch isn't making contact or the photo interrupter isn't already interrupted, now we can look for the front edge of the interrupter, or we can engage the switch. And so we reset a count variable. This is a temporary variable, and we print out a little message saying we're looking for the leading edge. Maybe I should have made it more ambiguous as far as or inclusive to using a physical switch too. Maybe for the next version. So we enter a while loop here between here and here, and what we do is we keep on doing a digital read on the pin home. And while it's not equals home tripped. So while the home pin, it doesn't equal whatever value you picked for a home tripped. And there's another condition which we have a double and while the count is less than the motor steps. So this ought to keep on repeating everything inside this loop. It will move the motor and step motor using the current pulse pin, whichever one that may be. Remember, we have more than one scenario, and using basically the motor pulse width. Almost all the movement in RDL is done with the same kind of high portion of the pulse train, and now we just use the setting motor delay fallback for the low portion of the pulse train, and we keep bumping up the counter. And if there's an error, obviously we break out of this loop, which should drop us back down to here. So we had reset the counter, and we kept on bumping up the counter, and one of our conditions is that the counter is less than motor steps. So to keep on doing this only until the counter is less than motor steps. And so if we reach the motor steps, then we might not have found it. So now we do a decision. We read the pin homing one more time to see if it's tripped, and if it's tripped, then we do everything inside this loop. If it's not, we tell the user that the home was not found. So now our motor's homed. It found the switch, or it found a photo interrupter, or the Hall effect sensor, whatever you have might have hooked up to for a homing sensor. So so it's homed. But what if home isn't quite right? What if you had mounted this thing a little weird? So I came up with this feature as such, that you can put in a number of steps that you could have it offset. So in other words, it can home, and then it could either go forward or backward just a little bit to make sure everything's just right. But you have to know in steps how many steps that would take, and that goes into the setting home offset member of the setting structure. So if what it does is copy that variable into val, and if it's not 0, then we put a little message saying we're going to offset, and then we either advance if it's greater than 0, else retard if it's less than 0. And what we do is keep on nudging the motor, checking for an error, and at the same time decrementing the val variable, and until it ends up being basically 0. And likewise, we would increment it if we want to retard. And anyway, once all the homing is done, we send a message that we're done. We do a position reset, because some of the like if you're in rotary mode, you might actually be on 1 when you're actually in 0 when you're homed up into this point. So we want to do a position reset. The cool thing about using these little tiny functions, and the bad thing is that it could end up being kind of old basics style spaghetti, or Fortran style spaghetti. But the good thing is that instead of putting a couple little things in a note saying what it is, I can save code and just say there's a function reset. Well, position reset. So not only say it's code, but it's easy to get your hand around an idea. So I like doing stuff like that. The next few commands are related, and the first two are very short, and that's go to start and go to end, and they're invoked by just typing in S for start or E for end, respectively. And we put a little message saying here what we're doing, and basically we take this variable location needed, and we copy in our setting structure. Do you remember that? And we grab the member variable limit start or limit end, respectively, and copy that into location needed. And now we should do a seek absolute with that location needed. and then it'll move the motor into that point. And once again, we do command equals command done just to make sure that we don't have any problems. The next command is go to absolute, and we run our line input function again with a prompt, and it gives us either a fresh command that you type in, or it gives us one of the arguments or the top argument that it copies into the command string object. Regardless, we take that command string object and we run one of the string object methods on it to float to convert it into a floating point number, which we then in turn put into the location requested. Now we're going to look at the location requested, and first thing we do is see if it's sane. So we look at the location requested and see if it's greater than the low range, and see if location requested is less than the high range. Then we can do something. But before we do, we need to check the software limits to make sure we're not outside the bounds. And if it's not limited, then we're going to put up a little line of text saying that we're going to go there. And we copy the location requested into the location needed and run our seek absolute. And if there's any problem in there, of course, we put out a little error message. And once again, we close with command equals command done. Oddly enough, the next command is called step. And the reason why that's odd is because RDL from its get-go I wrote to be operated using floating point numbers for both relative and absolute movements for both rotary and linear. So I've tried to abstract the user from the world of steps and having to calculate steps, but I thought there still might be some times when the user might want to type in a number of steps, although it's not perfectly accurate, because it's kind of funny that you kind of have to think one way or the other. Anyway, so I grab a line of text from using the line input command, which copies that text into the command string object, perhaps copying it as parameters from the arguments. And I use the toFloat method on the command string object to copy that numerical value into location requested. This next line turns this into either a turn or a distance-based offset. And then I use the sanity check-in just like before. You see range movement low, range movement high. These are the sanity check-in range variables. And I do a check on the software limits. If it's limited, it will give an error message. And if it's not limited, it will put up a little line of text saying it's going to step. And this time I use location change variable equals location requested for readability, and I do a seek relative using that location change. This next chunk of code handles three different commands. It handles turn, it handles degree, and it handles move. And formerly this was quite a few chunks of code, and when I was looking for redundancy in the code, this is where I found a lot of it. And I also had a thing where you can turn it by radians, but somebody had pointed out that who's going to want that? Anyway, the first thing I do, like before, is I check to make sure we're not dividing, and you've seen that. And here I take our command and make a copy of it, and this is just another string object. And this is one of the only places where this command copy actually even shows up. I think there's one other place. In this chunk of code here, basically what I'm doing is trying to pick out the right prompt for what the user might want to do. Like if the setting mode is mode linear, then we and the command copy equals M for move, then we put out this prompt. Otherwise, we'll put out these prompts, whether it's T for turn or D for degree. And once again, this saves a lot of code. Then we use our toFloat method on the command string object and place that into location requested. You can see I still think of these backwards. Sorry, that's the way I think. I kind of think, I guess, procedurally. I try to look procedurally and see what it's doing. So once again, I do some sanity checking here, and you've seen that before. If you want, you can look it over better. I check for software limits. This chunk of code lets us act on what the user had typed in further. So if it's not limited, then we're going to look at the command copy. And so it could be M for move, T for turn, and D for degree. And we put out the appropriate prompt here, here, or here. And for move or turn, we just make our location change, location requested. But if we're going to be turning by degrees, we've got to divide it by degree. And now we just call a seek relative with our change. And these were actually if it had fallen through before, and you've seen the end of this. I'd like to say a word of thanks to my friend Brett for helping me with this command, because I got really tripped up bad on this. And sometimes it was like standing at the base of a set of stairs, and I kept on pushing and pushing and pushing against it, but I was not rising to the occasion, nor was I running to the occasion. Anyway, so we've seen this kind of thing before, where we check our command and if structure, and we make sure we're not dividing, and we make sure that our limits aren't set. Now we look at our setting structure, and we look at the RPM member, and we see if it's anything more than 0, and otherwise it won't run, because you probably can't run with -negative RPM. Anyhow, actually maybe it should. Maybe it should go backwards. So maybe for the next version. Anyway. So here we calculate our period. It's 1/nth of our setting RPM divided by 60, and now we float that, and here we're dealing with microseconds, so we have to deal with that, and we have an issue that depending on what delays and like the pulse width and delay that you put in, that it might not be able to obtain that. And otherwise, I just use the setting motor, the fallback delay, and it'll print an error saying it's limited anyhow, at least that much. But we have another little problem in that our motor pulse width has to be subtracted from the impedance as well, or the total delay. And we set the motor direction to forward, and maybe for the next version I could do this so it can run backwards too. We'll see. And now we reset the error variable, and we print a line saying we're going to run. And now we keep on checking for an error. It could be an e-stop. It could be a keyboard stop. Not a software error, because it wouldn't have gotten this far. But anyway, we check for either an emergency stop, or a hardware limit stop, or a keyboard. So we keep on doing that. And while it's doing that, it'll keep on nudging using this impedance total, which is up here. And as soon as it gets done, it'll print out a message done for some unknown reason. I don't know why you needed that, but I put it in there anyhow. This is the speed limit if it's limited from up here. And then we have our few drop throughs, like limit mode and our division error. The next chunk of code also handles two commands, wake and sleep, and this code for this is pretty simple. If command equals wake, then we run the motor state with a wake, else we do it with a sleep, and then we do an EEPROM put at the very first byte our setting structure, and we write a message that the EEPROM was written to. The next two commands are pretty simple too. If you type an @ symbol, it calls show stats for where you're at, and the next one, if you type a period, it shows their settings. The kind of metaphor I was looking for is like in Unix, your parent directory, or where you're currently, at, if you can't use the @ symbol. So that's as close as I can get. Now you can see the help, and if you type a question mark, it returns this help. And there's a lot of memory used here, and this, you can see I only have one space in between here. I even looked at the names to try to figure out not only the descriptions but the names, to try to figure out how I can save memory here. There's a couple hundred bytes in here, and you can see that all the print lines, serial print lines, use the F option, and which saves a lot of memory in your data. And this program wouldn't be possible to fit inside a micro, definitely, without using that option. There's just not enough of data memory in it. And you can see I've got my message separator, and unfortunately this is actually in data, but it's used so much that it makes it handy. I don't particularly like the syntax of the F option. It's just, I wish there was like a print line F. I wish it was on the end of here instead, but I'm not going to get my way on this. Anyway, so if we had typed in a command, we had dropped down, we had processed it, we dropped down all the way down into here just before this little brace, and we needed a new command prompt. So we had already done all the code that handled the settings, and then we handled all the commands that weren't settings, and now we come to the third and final and shredded that section of code that handles the joystick. I tried to put a lot of thought into the joystick code. I wanted it to work with both division and non-division movement, and when you weren't dividing, I wanted it so to have a dead zone in the middle, and the farther you push the joystick, I wanted the motor to go faster and faster as you pushed it towards one side or another. Before we look at the joystick code, let's look at some of the variables and constants that deal with it. So if you scroll at the top, you can see that there's a section called Interface and Joystick, which I've highlighted. And you come across this thing that says constant boolean joystick enable equals false. And I had made a mistake in their previous RDL, and if you didn't hook up a joystick, the thing just ran on, and I'm sorry about that. Anyway, so the Arduino has a 10-bit analog to digital converter, which means that it returns values from 0 to 1023. And so I wanted the joystick to have a dead zone in it, and I figured out that like a 64 is a good value as far as a dead zone. So if you don't, because the detent might not be that good, or it might not be exactly in the middle, and you don't want the motor running on. So I picked out a 64 for a dead zone. And of course you could change all these or any of these. Next I have two thresholds. And one of them is the threshold. If you pass that point, the joystick will make the motor increase. And the other one is if you pull the joystick back, and if it passes that point, the joystick will decrease. And of course this 512 is in the center of the 1023, just about anyhow, of the joystick range. And then we add or subtract the dead zone from that. And also I've got an integer for the stick value. Then if you look in the setup in at least one other place, you can see I did some pre-calculation to figure out what nth of a unit the joystick increment would be. Going back down to the joystick section in the main loop, you can see there's a line that says if joystick enabled equals true. You can also do this. It's a kind of a style thing. But me personally, I would put a D on the end if I did that. I might do that. Who is to say? It doesn't make much of a difference as long as the result is readable and understandable and consistent. Anyway, we do an analog read on our joystick pin and place that into stick. And there's a line here. Likewise, there's a line here. If your joystick works backwards, just uncomment that. Now, we had predefined this joystick increase threshold before. And if the stick is greater than that, then it'll drop inside this little thing here. And first we check to see if we're dividing. And once again, the divisions is not only a variable, it's also kind of a switch at the same time. I like to, hypothetically, some programmers might have used a boolean to see if we're dividing as well, but what I did was use a 0 value to, if there's a 0 there, that means we're not dividing. But in this case, inside here, we would be dividing. So if we're dividing, if you move the joystick and you're dividing, you don't want it to go through all the divisions because you wouldn't be able to tell where one ended and the other began. So what you want to do is just trap the joystick. And so what we're going to do is keep this thing in here, inside this loop, as long as it keeps on increasing. So as soon as it stops increasing, it'll drop through here, and then it'll call division next. So if we're not dividing, it'll drop into this section right here. And now we just have to do a simple addition. We take our location requested equals our location, our current location, and we add the joystick increment we calculated before. We check to see, make sure we're inside limits, because it's kind of cool to be able to put like a soft stop on the joist, where, you know, like a destination point, like if we're winding a coil. And if we're not limited, then we're gonna take our impedance total. And this is kind of funny. I had a little issue with that, and I'll explain. So we do some mapping here, and the map function is a really handy thing. It's kind of a small bit of code that becomes a function, and I believe I wrote one once that worked with floating point numbers, or vice versa. Anyway, map is kind of a cool thing because it lets you scale variables, and we take our stick value. We take our joystick threshold for increase. We drop our total joystick amount, and we put our max delay and our joystick delay in here. And from that, we can scale the joystick. So we're scaling the joystick and making it proportional. So this is kind of tricky. It takes a little experimentation to get the code like this, and you can tell even by as I'm reading it out, I'm like, oh, how the hell did I do this? Anyway, so what we do then is we nudge we choose a direction, in this case forward, and we nudge the motor, and also we check for an error. And if there's no error, then we update our location, and we show the statistics, which will be like chunking through, kind of passing up the screen as we go in a crawl, as it were. And the joystick decreasing actually works the same way, but going the other way. And that's the code for the main loop. We're reaching the end of my coding video. I want to say again thanks to Brett for helping me through the run command. I want to say thank you for all my subscribers, and anyone who clicks on an ad or posts a comment, thanks a lot. You might be looking at my code saying that I know I can do better now, and I hope you can. I hope you go out and do it. And looking at my coding style as such, I tend to want to write legible, compact code, and that's where my emphasis is. And I use a lot of global variables to do that a lot. Maybe I should put G's in front of them or something like that, or come up with some system so other people could take part in this kind of project as well. But because there's so much I wanted to do and so little space, that this is how I decided to do it. And thanks for watching.